The universe began as a single, unimaginably dense point, a spark that ignited everything we know today. But here's the thing, what if that moment, the Big Bang, isn't the whole story? What if it's just the opening chapter of a saga far more intricate and awe-inspiring than we've ever imagined? For decades, we've held onto the idea that the universe started with a bang and has been expanding ever since. Yet, as we peer deeper into the cosmos, we're uncovering clues that suggest there's so much more to this tale. From the mysterious force of dark energy pushing galaxies apart to the mind-bending concept of multiverses where countless realities might exist, the story of our universe is being rewritten right before our eyes. And what lies ahead? Infinite possibilities, from the fate of stars to the potential for life beyond our own corner of space. This is not just a journey through time and space, it's a reimagining of everything we thought we knew. So let's dive in and explore how science is reshaping our understanding of the cosmos, one discovery at a time. The Big Bang is often painted as the ultimate beginning, a single, explosive moment that birthed the universe as we know it. And while it's true that this theory has withstood decades of scrutiny, offering a robust explanation for the expansion of the cosmos, it's far from the end of the story. Think of it more like the first stroke on a blank canvas, setting the stage for a masterpiece still being painted. The Big Bang tells us how the universe has evolved over billions of years, but it leaves us with tantalizing questions about what might have come before. What sparked that initial expansion? Was there something or someplace that existed before the Big Bang? These aren't just idle musings, they're the kind of questions that push scientists to the very edge of our understanding. Some theories suggest the possibility of a pre-Big Bang era, a cosmic landscape where conditions were entirely different from anything we've ever observed. Imagine a universe not born from nothing, but from the remnants of a previous cosmic cycle, like a phoenix rising from its own ashes. This idea, while still speculative, opens the door to a much larger conversation about the nature of existence itself. It's not just about rewriting the story of the universe, it's about realizing that the story might be far more complex and far more fascinating than we ever imagined. And as we explore these possibilities, we're not just looking back in time, we're also peering into the very fabric of reality, searching for clues that could reshape our understanding of everything. As we continue to unravel the mysteries of the universe, one of the most intriguing chapters in its history emerges: cosmic inflation. Picture this: immediately after the Big Bang, the universe didn't just expand, it exploded outward at an unimaginable rate, doubling in size over and over in the tiniest fraction of a second. This wasn't a gentle growth, it was a cosmic growth spurt so rapid that it's almost impossible to wrap our minds around. But why does this idea matter? Because it answers some of the most puzzling questions about the cosmos we see today. Take, for instance, the remarkable uniformity of the universe. No matter where we look, the temperature and distribution of matter are strikingly similar, even in regions that should have never been able to interact. Without inflation, this would be like finding two identical snowflakes on opposite sides of the Earth, a cosmic coincidence too unlikely to believe. Inflation explains this by proposing that these regions were once close together, expanding so quickly that they became evenly distributed before drifting apart. It's a theory that not only solves this mystery but also aligns beautifully with the patterns we observe in the cosmic microwave background, the faint afterglow of the Big Bang itself. Yet, as groundbreaking as inflation is, it doesn't answer everything. What triggered this rapid expansion, and what, if anything, came before it? Some scientists suggest that inflation might be just one piece of a much larger puzzle, hinting at even more fundamental processes at play. Could there have been a pre-inflationary era, a time when the rules of physics were entirely different? these questions lead us to the edges of our understanding, where theories like quantum gravity and multiverses begin to take shape. Cosmic inflation isn't just a scientific theory, it's a window into the earliest moments of existence, offering clues about how the universe grew from a single point to the vast, intricate web of galaxies we see today. But as we peer through this window, we're reminded that the story of the cosmos is far from complete. With every discovery, we're not just uncovering answers, we're also finding new questions, each one drawing us deeper into the mysteries of the universe. And in that journey, the possibilities are as infinite as the cosmos itself. Now, let's turn our attention to one of the greatest mysteries in modern cosmology: dark energy. This invisible force makes up an astonishing 68% of the universe, yet we still don't fully understand what it is. What we do know is that dark energy is the reason the universe isn't just expanding, it's expanding faster and faster over time. Imagine blowing up a balloon, but instead of slowing down as it gets bigger, it starts inflating even more rapidly. That's the effect dark energy has on the cosmos. But here's the twist: unlike gravity, which pulls things together, dark energy seems to push everything apart. It's as if the universe has an invisible engine, constantly revving up, driving galaxies away from each other at ever-increasing speeds. So, what exactly is this mysterious force? One leading idea is that dark energy is a cosmological constant, a kind of energy woven into the fabric of space itself. Albert Einstein first proposed this concept, though he later dismissed it as his greatest blunder. Ironically, modern observations suggest he might have been onto something. If dark energy is a cosmological constant, it would mean that empty space isn't truly empty. It's filled with a subtle, unchanging energy that subtly stretches the universe. But not everyone is convinced. Some scientists argue that dark energy might not be constant at all. Instead, it could be a dynamic field, something that changes over time or interacts with other forces in ways we haven't yet detected. Think of it like a thermostat for the universe, adjusting its influence as the cosmos evolves. This idea opens the door to even wilder possibilities, such as the potential for dark energy to weaken or strengthen in the distant future, altering the fate of the universe itself. Why does this matter? Because dark energy isn't just a scientific curiosity, it's a key piece of the puzzle in understanding the ultimate destiny of the cosmos. Will the universe keep expanding forever, tearing galaxies apart in a big rip? Or will dark energy's influence wane, allowing gravity to eventually pull everything back together in a big crunch? These aren't just hypothetical scenarios, they're questions that could redefine our understanding of reality. As we delve deeper into the nature of dark energy, we're not just exploring the mechanics of the universe, we're uncovering clues about its very essence. Every observation, every theory brings us closer to rewriting the story of the cosmos, a story that's still being written with every passing moment. And in that story, dark energy isn't just a footnote, it's one of the most compelling characters, shaping the universe in ways we're only beginning to comprehend. While dark energy is pushing the universe apart, there's another invisible force at work, quietly shaping the cosmos in ways we're only beginning to understand. This is dark matter, an enigmatic substance that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet, despite its elusive nature, dark matter's influence is everywhere. It's the unseen architect of the universe, holding galaxies together and sculpting the vast cosmic web that spans the cosmos. Without it, the universe as we know it wouldn't exist. So, how do we even know dark matter is there if we can't see it? The answer lies in its gravitational effects. When astronomers observe galaxies, they notice something strange. The stars on the outer edges are moving far too quickly for the amount of visible matter present. If only the matter we could see, stars, gas, and dust, were holding these galaxies together. They should have flown apart long ago, but they don't. Something invisible is providing the extra gravitational glue, and that something is dark matter. Think of it like this. Imagine watching a merry-go-round spin. You can't see the motor, but you know it's there because the ride keeps moving. Dark matter is the cosmic motor, unseen but essential, keeping galaxies and galaxy clusters intact. And its influence doesn't stop there. Dark matter also plays a crucial role in the formation of the universe's large-scale structure. After the Big Bang, tiny fluctuations in density allowed dark matter to clump together, creating gravitational wells that ordinary matter, like gas and dust, could fall into. Over billions of years, these clumps grew into the galaxies and galaxy clusters we see today. Yet, for all its importance, dark matter remains one of the greatest mysteries in science. What is it made of? Is it a particle like the ones in the standard model of physics, or something entirely new? Scientists have proposed numerous candidates, from weakly interacting massive particles, aptly called WIMP, to actions, hypothetical particles that could solve multiple cosmic puzzles at once. Efforts to detect dark matter are ongoing, with experiments deep underground and in space searching for even the faintest hints of its presence. So far, no direct detection has been confirmed, but the search itself is transforming our understanding of the universe. Every experiment, every observation brings us closer to uncovering the true nature of this invisible architect. And here's where it gets even more fascinating. Dark matter might not just be shaping the universe, it could also hold clues to its ultimate fate. Some theories suggest that dark matter interacts with dark energy in ways we don't yet understand, potentially influencing the expansion of the cosmos over billions of years. Could dark matter be the key to unlocking the universe's final destiny? As we continue to explore the mysteries of dark matter, we're not just solving a scientific puzzle, we're rewriting the story of the cosmos. This invisible force, though hidden from our eyes, is shaping the universe in profound ways, reminding us that there's so much more to discover. And in that discovery lies the potential to redefine our understanding of reality itself. What if everything we see around us, the stars, galaxies, and even the laws of physics, is just one small part of a much grander picture? This is the tantalizing idea behind the multiverse theory, a concept that suggests our universe might be just one of many. Picture an endless cosmic tapestry where each thread represents a separate universe, each with its own unique set of rules, its own history, and perhaps even its own version of reality. It's a mind-bending idea, but one that has gained serious traction among scientists in recent years. The multiverse theory isn't just a single idea, it comes in several flavors, each offering a different perspective on how these other universes might exist. One of the most popular versions is the bubble universe model, which suggests that during the rapid expansion of the early universe, different regions of space could have inflated at different rates, creating isolated pockets of reality. These bubbles would be entirely separate from our own, with their own physical constants and laws of nature. Imagine blowing soap bubbles, each floating independently, never touching or interacting. That's the kind of cosmic isolation we're talking about, but bubble universes are just the beginning. Another intriguing possibility is the idea of parallel realities, where every decision you've ever made spawns a new universe. Did you choose coffee over tea this morning? In another universe, there's a version of you sipping tea instead. While this idea might sound like science fiction, it's rooted in the principles of quantum mechanics, where every possible outcome of an event exists simultaneously until it's observed. So, is the multiverse science or speculation? The truth is, it's a bit of both. On one hand, the multiverse theory provides elegant solutions to some of the biggest questions in physics, like why the fundamental constants of nature seem so finely tuned for life. If there are infinite universes, each with different laws, it's not surprising that at least one of them, ours, happens to be just right for us. On the other hand, the multiverse is notoriously difficult to test. After all, how do you observe something that exists beyond the boundaries of our own universe? Despite these challenges, the multiverse remains a powerful tool for exploring the deepest mysteries of existence. It challenges us to think beyond what we can see and measure, to imagine a reality far more vast and complex than we ever dreamed. And as we continue to probe the edges of our understanding, the multiverse theory reminds us that the cosmos is full of possibilities, some within reach and some that may forever remain just beyond our grasp. This idea doesn't just reshape our view of the universe, it reshapes our view of ourselves. If there are infinite versions of reality, what does that mean for our place in the cosmos? Are we unique or just one of countless iterations? These questions don't just belong to scientists, they invite all of us to ponder the nature of existence itself. And in that exploration, we're not just uncovering the secrets of the universe, we're also uncovering the endless potential of our own curiosity. The universe as we know it, vast, intricate, and teeming with galaxies, owes its existence to something astonishingly small: quantum fluctuations. In the earliest moments after the Big Bang, the cosmos wasn't the smooth, uniform expanse we might imagine. Instead, it was a seething sea of uncertainty, where tiny, random ripples in the fabric of space and time began to take shape. These ripples, born from the strange rules of quantum mechanics, might seem insignificant at first glance, but here's the remarkable part: they were the seeds from which the entire cosmic structure grew. To understand how this works, let's take a closer look at those early moments. Picture the universe as a simmering pot of soup, with bubbles of energy constantly forming and popping. In the same way, quantum fluctuations caused minuscule variations in density, some regions slightly denser, others slightly less dense. At the time, these differences were unimaginably small, but as the universe expanded, they began to grow. Gravity played a crucial role here, pulling matter toward the denser regions, amplifying those tiny differences over billions of years. What started as microscopic ripples eventually became the building blocks of galaxies, stars, and even the vast cosmic web that connects everything in the universe. Here's where it gets even more fascinating. Without these fluctuations, the universe might have remained a featureless void. The slight irregularities in density gave gravity something to work with, creating the scaffolding for everything we see today. It's like throwing a handful of pebbles into a still pond. The ripples spread out, interact, and create patterns. In the cosmos, those patterns became the clusters of galaxies and the voids between them, forming a structure so vast it's almost beyond comprehension. But what caused these fluctuations in the first place? The answer lies in the quantum nature of reality itself. At the smallest scales, particles don't behave like tiny billiard balls. They exist in a state of constant uncertainty, popping in and out of existence in a dance governed by probability. This inherent randomness, amplified by the rapid expansion of the early universe, left behind a faint but indelible imprint, one we can still see today in the cosmic microwave background, the afterglow of the Big Bang. This discovery isn't just a triumph of science, it's a testament to the interconnectedness of the cosmos. The same quantum rules that govern particles in a lab also shape the largest structures in the universe. It's a reminder that the universe operates on all scales, from the infinitesimally small to the unimaginably large. And as we continue to study these fluctuations, we're not just uncovering the origins of galaxies, we're peering into the very heart of creation itself. Quantum fluctuations are more than just a cosmic curiosity. They're the blueprint of the universe. Every star, every galaxy, every filament of the cosmic web traces its origins back to those tiny ripples in the early universe. And as we map these structures with ever greater precision, we're not just telling the story of how the cosmos came to be, we're also asking profound questions about the nature of reality itself. What other secrets do these fluctuations hold? Could they reveal clues about the universe's ultimate fate? The answers are still out there, waiting to be discovered. Imagine holding a photograph of yourself as a baby, a snapshot that captures the earliest moments of your existence. Now picture the universe having its own version of that photograph. That's exactly what the cosmic microwave background, or CMB, is: a faint glow of light that serves as a cosmic baby picture, a window into the universe's infancy. This ancient light, which has traveled across space and time for over 13 billion years, is one of the most profound discoveries in modern cosmology. It's not just light, it's a time capsule carrying secrets from a time when the universe was just 380,000 years old. To understand why the CMB is so special, let's rewind to those early moments. After the Big Bang, the universe was a seething, opaque soup of particles and energy. Light couldn't travel freely because it was constantly bouncing off free electrons like a game of cosmic pinball. But around 380,000 years later, the universe had cooled enough for electrons and protons to combine into neutral atoms. Suddenly, light could travel unimpeded and the universe became transparent. That first burst of light, now stretched and cooled by the expansion of the cosmos, is what we detect today as the CMB. What's remarkable about this ancient light is how much it tells us. When scientists first discovered the CMB in the 1960s, it was a eureka moment, a smoking gun for the Big Bang theory. But it didn't stop there. As technology advanced, missions like the Planck satellite mapped the CMB in exquisite detail, revealing tiny temperature fluctuations, imprints of the universe's earliest moments. These fluctuations are like cosmic fingerprints, showing us where matter was slightly denser or less dense. Over billions of years, those tiny differences grew into the galaxies, stars, and cosmic structures we see today. But the CMB doesn't just tell us about the universe's structure, it also holds clues about its composition. By analyzing the patterns in this ancient light, scientists have determined that ordinary matter, the stuff we're made of, makes up only about 5% of the universe. The rest is dark matter and dark energy, those mysterious forces we've been exploring. The CMB is like a cosmic Rosetta Stone, helping us decode the universe's hidden language. And then there's the question of what came before. The CMB gives us a glimpse of the universe at 380,000 years old, but what about the time before that? Could the CMB hold hints about the universe's very first moments, or even what sparked the Big Bang itself? Some scientists believe that subtle patterns in the CMB might reveal traces of cosmic inflation, that rapid expansion we discussed earlier. Others are searching for faint imprints of gravitational waves, ripples in spacetime that could point to even earlier events. The cosmic microwave background is more than just a relic, it's a roadmap to the universe's past. It connects us to a time when the cosmos was young, offering insights into how it began and how it evolved. But it's also a reminder of how much we still have to learn. Every new observation, every refined measurement brings us closer to understanding the universe's deepest mysteries. And as we continue to study this ancient light, we're not just looking back in time, we're also uncovering the story of how everything came to be, one photon at a time. Black holes, those enigmatic regions of space where gravity is so intense that not even light can escape, are far more than just cosmic vacuum cleaners. They're cosmic laboratories, places where the laws of physics are pushed to their limits, revealing clues about the universe that we can't find anywhere else. But what makes black holes so fascinating isn't just their destructive power. It's their potential to unlock entirely new realms of understanding. Let's start with the basics. Black holes are born from the collapse of massive stars. When a star many times larger than our Sun exhausts its fuel, it collapses under its own gravity, creating a region of space so dense that it warps space-time itself. This process doesn't just create a black hole, it also plays a crucial role in the formation of galaxies, supermassive black holes which can weigh millions or even billions of times more than our Sun, often sit at the center of galaxies, including our own Milky Way. These cosmic giants don't just exist passively, they actively shape their surroundings, influencing the motion of stars and gas, and even triggering the birth of new stars. But it's what lies inside a black hole that truly captures the imagination. Beyond the event horizon, the point of no return, our understanding of physics breaks down. The intense gravitational forces crush matter into an infinitely dense point called a singularity, where the laws of space and time as we know them cease to exist. Here, the rules of general relativity and quantum mechanics collide, creating a puzzle that scientists are still trying to solve. Some theories suggest that singularities might not be the end of the story. Instead, they could be gateways to other universes or dimensions where the fabric of reality is entirely different from our own. This idea isn't just science fiction. The concept of a black hole as a portal stems from the work of physicists like Stephen Hawking and Kip Thorne, who explored the possibility of wormholes, theoretical tunnels through space-time that could connect distant parts of the universe or even different universes altogether. While no evidence of wormholes exists, the mathematics behind them is compelling enough to spark serious scientific inquiry. Imagine a scenario where a black hole's singularity doesn't lead to destruction, but to an entirely new reality, one with its own laws of physics and perhaps even its own forms of life. Of course, the idea of black holes as gateways comes with its own set of challenges. The intense gravitational forces near a singularity would likely tear apart anything that ventured too close, making travel through a black hole seem impossible. But here's the twist. Some theories suggest that certain types of black holes, like rotating ones known as Kerr black holes, might have more navigable interiors. These black holes could potentially offer safe passage through their centers, opening up the tantalizing possibility of interstellar or even interuniversal travel. Black holes are more than just cosmic oddities. They're windows into the unknown. They challenge us to rethink our understanding of space, time, and reality itself. As we continue to study these mysterious objects, we're not just exploring the limits of science, we're also asking profound questions about the nature of existence. Could black holes really be gateways to new realities? The answer, like the black holes themselves, lies hidden in the shadows, waiting to be uncovered. And in that search, we're reminded that the universe is full of mysteries, each one more fascinating than the last. The Big Bang is often seen as the ultimate starting point, the moment when time itself began. But what if it wasn't the true beginning? What if the universe's story extends even further back into a realm that existed before time as we know it? This is the tantalizing question that leads us into the realm of time before time, a concept that challenges our very understanding of existence. One of the most intriguing ideas is the Big Bounce theory, which suggests that the Big Bang wasn't the start of everything but rather a rebirth. Imagine the universe as a cosmic accordion, expanding and contracting over and over in an endless cycle. According to this theory, our universe might have been born from the collapse of a previous one, a process that repeats indefinitely. Instead of a single, explosive beginning, the universe could be part of an eternal rhythm, a cosmic heartbeat, if you will. This idea not only redefines the Big Bang, but also opens the door to a universe with no true beginning or end, just an ongoing dance of creation and destruction. Another compelling perspective comes from the concept of cyclic universes. In this view, the universe undergoes endless cycles of expansion and contraction, each cycle leaving behind subtle imprints that could influence the next. Think of it like a cosmic etch-a-sketch, where each cycle erases the previous one but leaves faint traces of what came before. These traces, if we could detect them, might hold clues about the universe's ultimate nature and its infinite potential for renewal. But what about the idea that time itself might not have existed before the Big Bang? This is where quantum gravity comes into play. At the smallest scales, the rules of gravity and quantum mechanics merge, creating a frothy, chaotic state where time and space lose their usual meaning. In this quantum realm, the concept of before might not even apply. Instead, the universe could have emerged from a timeless, spaceless state, a cosmic soup of potential waiting to burst into existence. These theories don't just challenge our understanding of the universe, they also invite us to rethink our place within it. If the Big Bang wasn't the absolute beginning, what does that mean for the story of existence? Could there be echoes of previous universes hidden in the fabric of reality, waiting to be discovered? As we explore these ideas, we're not just looking for answers, we're expanding the boundaries of what we thought was possible. The concept of a time before time reminds us that the universe is far more mysterious and complex than we've ever imagined. And in that mystery lies the potential for endless discovery, a journey that continues to rewrite the story of everything we know. What if everything we see, touch, and experience, the stars, planets, and even ourselves, is nothing more than a projection? This is the startling premise of the holographic principle, a theory that challenges our most fundamental assumptions about reality. At its core, the holographic principle suggests that the entire universe might be a kind of cosmic hologram, where all the information about everything that exists is encoded not within the three-dimensional space we inhabit, but on a two-dimensional surface at its boundary. It's a concept so radical that it feels like something out of science fiction, yet it's grounded in serious scientific thought. To understand this idea, let's start with something familiar, a hologram. You've probably seen holograms before, those shimmering, 3D images that seem to float in midair. What makes them fascinating is that they're created by encoding information on a flat surface like a piece of film. When light hits that surface, it reconstructs the image in 3 dimensions. Now, imagine scaling this up to the size of the universe. The holographic principle proposes that the cosmos works in a similar way. All the information about every particle, every galaxy, and every interaction could be encoded on a distant, two-dimensional boundary, like the surface of a black hole's event horizon or the edge of the observable universe. What we perceive as a three-dimensional reality might just be a projection of that encoded data. But why would scientists propose something so bizarre? It all ties back to black holes. In the 1970s, physicist Jacob Bekenstein discovered that the amount of information a black hole can contain is proportional to its surface area, not its volume. This was a groundbreaking insight because it suggested that the information about everything that falls into a black hole isn't lost, it's stored on its boundary. Later, physicist Leonard Susskind and others expanded this idea, proposing that the entire universe might operate on the same principle. If a black hole can encode information on its surface, why not the cosmos itself? This leads to some mind-bending implications. If the holographic principle is correct, then the three-dimensional world we experience could be an illusion, a kind of cosmic mirage. Every event, every particle, every law of physics might be nothing more than a projection of information stored elsewhere. It's as if the universe is a giant movie screen, and we're the characters living within the film, unaware that we're part of a larger, more complex reality. So how do we test such an extraordinary idea? One approach is through the study of quantum gravity, which seeks to unify the laws of quantum mechanics and general relativity. The holographic principle offers a potential bridge between these two theories, suggesting that the fabric of spacetime itself might emerge from quantum information encoded on a lower dimensional surface. Experiments in particle physics and cosmology, like those conducted at the Large Hadron Collider or through observations of the cosmic microwave background, could provide clues that support or refute this theory. The holographic principle doesn't just challenge our understanding of space and time, it also raises profound questions about the nature of existence. If the universe is a hologram, what does that mean for free will, consciousness, or even the concept of reality itself? Are we merely characters in a cosmic simulation, or is there something more fundamental at play? These questions don't just belong to physicists, they invite all of us to rethink our place in the cosmos. As we explore this fascinating idea, we're reminded that the universe is far stranger and more mysterious than we often assume. The holographic principle isn't just a scientific theory, it's a window into a deeper understanding of reality, one that could reshape everything we think we know. And in that exploration, we're not just uncovering the secrets of the cosmos, we're also discovering the boundless potential of human curiosity to imagine, question, and dream. What if the universe's deepest mysteries, gravity, light, matter, and energy, could all be explained by one elegant idea? This is the ambitious promise of string theory, a revolutionary framework that seeks to unify the fundamental forces of nature into a single, cohesive picture. At its heart, string theory proposes that everything in the universe, from the tiniest particles to the vastest galaxies, is made up of incredibly small, vibrating strings. These strings aren't like the ones you'd find on a guitar. They're one-dimensional filaments of energy, each vibrating at a unique frequency that determines the properties of the particle it creates. This idea might sound simple, but its implications are profound. For decades, physicists have struggled to reconcile the two great pillars of modern science: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the force of gravity on cosmic scales. These two theories work beautifully in their own domains, but when it comes to understanding extreme environments like the center of a black hole or the first moments after the Big Bang, they clash violently. String theory offers a potential solution, weaving these disparate threads into a single tapestry. One of the most exciting aspects of string theory is its ability to describe all known particles and forces as different manifestations of these vibrating strings. A string vibrating one way might produce an electron, while another frequency creates a photon, the particle of light. Even gravity, which has resisted integration into quantum mechanics for so long, emerges naturally from this framework. In essence, string theory suggests that the universe's complexity arises from the harmony of these tiny strings, much like a symphony emerges from the interplay of individual notes. But string theory isn't without its challenges. For one, it requires the existence of extra dimensions, not just the 3 spatial dimensions we're familiar with, but potentially 10 or more. These extra dimensions are thought to be curled up so tightly that they're invisible to us, much like the way a garden hose looks like a one-dimensional line from a distance, but reveals its true cylindrical shape up close. While this idea is mathematically elegant, it's also incredibly difficult to test experimentally. After all, how do you detect something that's hidden on such an unimaginably small scale? Another hurdle is the sheer complexity of the math involved. String theory is a playground for theoretical physicists, but its equations are so intricate that even the most advanced computers struggle to solve them. And without experimental evidence, some critics argue that string theory remains more of a beautiful idea than a proven science. Yet, despite these challenges, string theory continues to captivate scientists and science enthusiasts alike. It's not just a theory about the universe, it's a quest to uncover its deepest truths. By attempting to unify all forces and particles into a single framework, string theory challenges us to think beyond the boundaries of our current understanding. It invites us to imagine a universe where everything, every star, every atom, every force is interconnected, a cosmic dance of vibrating strings that echoes through the fabric of reality. As we explore this fascinating theory, we're reminded that science is as much about the journey as it is about the destination. String theory may not yet have all the answers, but it's pushing the boundaries of what we thought was possible, opening doors to new ways of thinking about the universe. And in that exploration, we're not just rewriting the story of the cosmos, we're also discovering the limitless potential of human curiosity to dream, to question, and to uncover the secrets of existence itself. As we gaze into the vast expanse of the universe, it's hard not to wonder, how will it all end? The fate of the cosmos is one of the most profound questions in science, and the answer hinges on a delicate balance between forces we're only beginning to understand. Will the universe continue expanding forever, stretching into an endless cold void? Or will gravity eventually win the cosmic tug of war, pulling everything back into a fiery collapse? These two possibilities, known as the heat death and the big crunch, offer starkly different visions of the universe's ultimate destiny. Let's start with the heat death scenario, often described as the cold end of the universe. In this view, the expansion driven by dark energy continues unchecked, pushing galaxies farther and farther apart. Over trillions of years, stars will burn out, black holes will evaporate, and matter itself will decay into its most basic components. The universe will become a vast, dark, and lifeless expanse where temperatures approach absolute zero, a state of maximum entropy where no energy remains to power any meaningful activity. This isn't just a poetic metaphor, it's a scientifically plausible outcome based on our current understanding of thermodynamics and cosmology. But what if the universe doesn't expand forever? Enter the Big Crunch, a dramatic alternative where gravity eventually overcomes dark energy's push. In this scenario, the expansion slows, stops, and then reverses, pulling galaxies, stars, and even atoms back together. The universe would collapse into an ultra-dense state, resembling the conditions of the Big Bang in reverse. Some theories suggest this could lead to a big bounce, where the universe rebounds into a new cycle of expansion and contraction, creating an endless loop of cosmic rebirth. So, which of these fates is more likely? The answer lies in the tug of war between dark energy and gravity. Current observations suggest that dark energy is winning, causing the universe to expand at an accelerating rate. But there's still much we don't know. Could dark energy's influence change over time? Could new forces or particles emerge that alter the balance? These questions keep scientists on the edge of their seats, as every new discovery has the potential to reshape our understanding of the cosmos's ultimate fate. What makes these scenarios so captivating isn't just their scientific implications, it's what they reveal about the nature of existence itself. Whether the universe ends in a cold, silent fade or a fiery collapse, these possibilities remind us of the impermanence of everything we know. They challenge us to think beyond our own lifetimes, even beyond the lifespan of stars and galaxies, and to consider the universe as a dynamic, evolving entity with a story that's still being written. As we ponder these cosmic destinies, we're not just exploring the end of the universe, we're also uncovering the infinite mysteries that define it. Each theory, each observation, brings us closer to understanding not just how the universe might end, but how it came to be in the first place. And in that journey, we're reminded that the cosmos is as much a story of beginnings as it is of endings, a tale that continues to unfold with every passing moment. The universe isn't just a vast expanse of stars and galaxies, it's also a treasure trove of worlds waiting to be discovered. Over the past few decades, astronomers have uncovered thousands of planets orbiting stars beyond our solar system, known as exoplanets. These distant worlds, some eerily similar to Earth and others wildly different, have opened up a new frontier in our search for life beyond our own planet. The discovery of exoplanets isn't just a scientific milestone, it's a profound shift in how we see our place in the cosmos. Take, for instance, the first confirmed exoplanet discovered in 1992, a world orbiting a pulsar, a type of dead star. At the time, it seemed like a cosmic oddity, but it was just the beginning. Since then, we've found planets of all shapes and sizes, gas giants larger than Jupiter, rocky worlds with molten surfaces, and even super-Earths that might combine the best features of rocky and gaseous planets. But the real excitement lies in the hunt for Earth-like planets, worlds that could potentially support life as we know it. One of the most promising discoveries came in 2015, when NASA's Kepler mission revealed a planet named Kepler 452b. Located within its star's habitable zone, the region where temperatures could allow liquid water to exist, this planet quickly earned the nickname Earth's cousin. While it's too far away to study in detail, its discovery sparked a tantalizing question. Could there be other Earths out there teeming with life? The search for life on exoplanets isn't just about finding water or the right temperature. Scientists are also looking for biosignatures, chemical markers in a planet's atmosphere that could indicate the presence of life. Oxygen, for example, is a strong candidate because it's produced by living organisms on Earth. But what if life elsewhere doesn't follow the same rules? Some researchers are exploring the possibility of weird life, organisms that thrive in environments we consider inhospitable, like planets with methane atmospheres or extreme temperatures. This search is being revolutionized by cutting-edge technology. The James Webb Space Telescope, launched in 2021, is designed to analyze the atmospheres of distant exoplanets in unprecedented detail. By studying the starlight that filters through these atmospheres, scientists can identify the chemical fingerprints of potential life. It's like having a cosmic detective that can sniff out clues from light years away. But the implications of exoplanet discoveries go beyond the search for life. They're also reshaping our understanding of how planets form and evolve. For example, the existence of hot Jupiters, gas giants orbiting dangerously close to their stars, challenged traditional theories of planetary formation. These discoveries have forced scientists to rethink the processes that shape planetary systems, including our own. As we continue to explore these distant worlds, we're not just looking for life, we're also uncovering the incredible diversity of the universe. Each exoplanet tells a story, whether it's a fiery super-Earth with skies of molten rock or a frozen world shrouded in ice. And with every discovery, we're reminded that the universe is far more dynamic and full of possibilities than we ever imagined. The search for exoplanets is more than a scientific endeavor. It's a journey of curiosity and wonder. It challenges us to think beyond our own world and to imagine what might lie in the uncharted reaches of space. Are we alone, or is the cosmos teeming with life? The answer, like the stars themselves, is still waiting to be found. And in that search, we're not just exploring the universe, we're also discovering the boundless potential of our own imagination. When we think of life, we often picture lush forests, vast oceans, or even bustling cities. But life on Earth isn't confined to these familiar settings. It's far more resilient and resourceful than we once imagined. In some of the most extreme environments on our planet, from the scalding heat of deep-sea hydrothermal vents to the frozen deserts of Antarctica, organisms known as extremophiles not only survive but thrive. These remarkable life forms are rewriting the rules of biology, and in doing so, they're transforming how we search for life beyond Earth. Take, for instance, the bacteria living in the boiling waters of hydrothermal vents miles beneath the ocean surface. These vents, often called black smokers, spew superheated water rich in minerals, creating an environment that seems utterly hostile to life. Yet here, entire ecosystems flourish, supported by chemosynthetic bacteria that convert chemicals like hydrogen sulfide into energy, completely independent of sunlight. These microbes are the foundation of a food chain that includes giant tube worms, crabs, and other creatures, proving that life can adapt to conditions we once thought were impossible. But it's not just heat that extremophiles can handle. In the icy depths of Antarctica's Lake Vostok, buried beneath miles of glacial ice, scientists have discovered microbes that survive in near-total darkness and sub-zero temperatures. These organisms have adapted to an environment with almost no nutrients, relying on unique metabolic processes to eke out an existence. What's even more astonishing is that similar conditions exist on icy moons like Europa and Enceladus, where subsurface oceans might harbor life beneath frozen crust. If extremophiles can thrive in Earth's harshest environments, why couldn't life exist in the icy oceans of these distant worlds? Another fascinating example comes from the acidic hot springs of Yellowstone National Park. Here, microorganisms known as thermophiles thrive in water that's both scorching hot and highly acidic, conditions that would be fatal to most life forms. These microbes have evolved specialized proteins and enzymes that allow them to function in environments that would destroy the cellular machinery of other organisms. Their existence suggests that life might not need the Goldilocks conditions we often associate with habitability. Just the right temperature, just the right pH. Instead, life might find a way to adapt to almost any environment, no matter how extreme. These discoveries aren't just scientific curiosities, they're reshaping our understanding of where life can exist both on Earth and beyond. If life can survive in the crushing pressures of the deep ocean, the freezing darkness of Antarctica, and the scorching acidity of hot springs, then the possibilities for life elsewhere in the universe are nearly limitless. Suddenly, the icy moons of Jupiter and Saturn, the subsurface oceans of distant exoplanets, and even the harsh environments of Mars don't seem so inhospitable after all. Astrobiology, the study of life in the universe, is deeply rooted in these findings. By studying extremophiles, scientists are developing new tools and techniques to search for life in places we once thought were barren. For example, missions to Mars now include instruments designed to detect microbial life that might resemble Earth's extremophiles. Similarly, future missions to Europa and Enceladus will look for signs of life in their subsurface oceans, guided by what we've learned from Earth's harshest environments. What makes this research so exciting is that it's not just about finding life. It's about understanding the incredible adaptability and resilience of living organisms. Every discovery of an extremophile on Earth expands the boundaries of where we might expect to find life in the universe. It's a reminder that life, in all its forms, is not just a product of its environment but a force that can shape and adapt to it, even in the most unlikely places. As we continue to explore the cosmos, these insights will guide us, not just in where we look, but in how we think about the potential for life. The story of the universe is no longer just about stars and planets. It's about the incredible diversity of life, both on Earth and potentially beyond. And in that story, extremophiles are not just survivors. They're pioneers, showing us that life's potential is as vast and varied as the universe itself. The universe has always been a canvas of mysteries, but it's our tools, our eyes on the cosmos, that bring its secrets into focus. Over the past few decades, technological leaps in telescopes and space missions have transformed our understanding of the universe, revealing details we once thought were beyond our reach. From the depths of distant galaxies to the faint glow of ancient light, these instruments are rewriting the story of the cosmos, one discovery at a time. At the forefront of this revolution is the James Webb Space Telescope, often called JWST. Launched in 2021, this marvel of engineering is more than just a telescope, it's a time machine. Unlike its predecessor, the Hubble Space Telescope, which primarily observed visible light, JWST is designed to peer into the infrared spectrum. This allows it to see through cosmic dust and capture light from the earliest moments of the universe, when the first stars and galaxies were forming. Imagine looking back over 13 billion years, almost to the dawn of time itself. That's the power of JWST, and it's already delivering breathtaking results, from stunning images of distant nebulae to unprecedented insights into the atmospheres of exoplanets. But JWST isn't alone in this cosmic exploration. Missions like the Hubble Space Telescope, which has been orbiting Earth since 1990, continue to provide invaluable data. Hubble's iconic images, like the Pillars of Creation in the Eagle Nebula, have not only captivated the public but also deepened our scientific understanding of star formation and galactic evolution. Even today, Hubble remains a vital tool, complementing JWST infrared capabilities with its own observations in visible and ultraviolet light. Together, these telescopes offer a more complete picture of the universe, each filling in gaps the other can't reach. Then there's the Transiting Exoplanet Survey Satellite, or TESS, which is revolutionizing the search for planets beyond our solar system. By monitoring the brightness of nearby stars, TESS detects tiny dips in light caused by planets passing in front of them. This method, known as the transit technique, has already identified thousands of exoplanet candidates, some of which might harbor conditions suitable for life. TESS is like a cosmic census taker, cataloging worlds that could one day be studied in greater detail by telescopes like JWST. And let's not forget the European Space Agency's Gaia mission, which is mapping the Milky Way in unprecedented detail. By measuring the positions, distances, and motions of over 1 billion stars, Gaia is helping us understand the structure and history of our own galaxy. It's like creating a 3D map of the Milky Way, revealing its past collisions, its spiral arms, and even the remnants of ancient galaxies it has absorbed over billions of years. These missions, and many others, are more than just technological achievements, they're gateways to discovery. Each one brings us closer to answering fundamental questions about the universe. How did galaxies form? What are the conditions for life? And what lies beyond the boundaries of our current knowledge? They remind us that the cosmos isn't just a static backdrop. It's a dynamic, evolving story, and we're just beginning to read its pages. As we continue to push the boundaries of technology, we're not just exploring the universe, we're redefining what's possible. Every image, every data point, every new discovery adds another piece to the puzzle, bringing us closer to understanding the grand tapestry of existence. And in that journey, we're reminded that the universe isn't just out there, it's within us, a story we're all a part of, written in starlight and shaped by curiosity. Artificial intelligence is no longer confined to sci-fi movies or tech labs. It's now a powerful tool reshaping the way we explore the cosmos. In the field of cosmology, where the sheer volume of data can overwhelm even the most seasoned scientists, AI is stepping in to uncover patterns and insights that were once hidden in the noise. From sifting through terabytes of telescope images to predicting the behavior of distant galaxies, machine learning is becoming an indispensable partner in our quest to understand the universe. One of the most exciting applications of AI in cosmology is its ability to process vast amounts of data at lightning speed. Take, for example, the petabytes of information collected by telescopes like the James Webb Space Telescope or the Large Synoptic Survey Telescope. These instruments capture an astonishing amount of data, far more than any human team could analyze in a lifetime. That's where AI comes in. Machine learning algorithms can scan through this data, identifying subtle patterns and anomalies that might otherwise go unnoticed. It's like having a tireless assistant that never sleeps, tirelessly searching for cosmic needles in a galactic haystack. But AI isn't just about speed, it's also about precision. In cosmology, even the tiniest details can lead to groundbreaking discoveries. For instance, AI has been used to analyze the cosmic microwave background, the faint afterglow of the Big Bang. By training algorithms to detect minute variations in this ancient light, scientists have gained new insights into the early universe's structure and composition. These findings aren't just academic, they're helping us refine our understanding of how the universe evolved and what its ultimate fate might be. Another area where AI is making waves is in the search for exoplanets. Traditional methods of finding planets involve painstakingly analyzing light curves from stars, looking for the telltale dips that indicate a planet passing by. This process can be slow and labor-intensive, but AI is changing the game. Machine learning models can quickly sift through thousands of light curves, identifying potential exoplanet candidates with remarkable accuracy. In fact, some of the most promising exoplanet discoveries in recent years have been made with the help of AI, proving that machines and humans make a powerful team. AI is also helping us tackle some of cosmology's biggest mysteries, like dark matter and dark energy. These invisible forces make up the majority of the universe, yet we know very little about them. By analyzing the distribution of galaxies and the way light bends around massive objects, AI algorithms are helping scientists map the invisible scaffolding of the cosmos. These maps not only shed light on the nature of dark matter and dark energy, but also provide clues about the universe's large-scale structure and evolution. What's truly remarkable about AI's role in cosmology is its ability to adapt and learn. Unlike traditional software, which follows predefined rules, machine learning algorithms improve over time as they process more data. This means that as our telescopes collect more information, AI becomes even better at identifying patterns and making predictions. It's a virtuous cycle where each discovery fuels the next, pushing the boundaries of what we thought was possible. As we integrate AI into cosmology, we're not just enhancing our tools, we're transforming how we think about the universe. AI allows us to ask new questions, explore new possibilities, and uncover connections that might have remained hidden. It's a reminder that the story of the cosmos isn't just about what we can see or measure. It's also about how we interpret and understand the vast, intricate tapestry of existence. And in that journey, AI is proving to be an invaluable ally, helping us rewrite the story of the universe one algorithm at a time. Mathematics isn't just a tool for solving problems, it's the very language the universe speaks. From the graceful arc of a planet's orbit to the chaotic dance of galaxies, the cosmos operates on mathematical principles so precise that they can be described with elegant equations. It's as if the universe wrote its own rulebook, and mathematics is our way of deciphering it. Without this universal language, our understanding of the cosmos would be like trying to read a book in a language we've never learned. Take gravity, for example. Isaac Newton's law of universal gravitation was one of the first major breakthroughs in using mathematics to describe a fundamental force of nature. His equation not only explained why apples fall from trees, but also predicted the motion of planets with stunning accuracy. Later, Albert Einstein's theory of general relativity took this even further, using complex mathematical frameworks to describe gravity as the curvature of spacetime itself. These equations didn't just explain what we could see, they predicted phenomena like black holes and gravitational waves long before we had the technology to observe them. But mathematics doesn't just describe the cosmos, it also helps us uncover its hidden patterns. Consider the Fibonacci sequence, a series of numbers where each is the sum of the two preceding ones. This sequence appears everywhere in nature, from the spirals of galaxies to the arrangement of leaves on a stem. It's as if the universe has a built-in rhythm, a mathematical heartbeat that echoes through the fabric of existence. By studying these patterns, we're not just observing the universe, we're tapping into its underlying logic. The power of mathematics becomes even more apparent when we look at the quantum world. At this scale, particles don't behave like tiny billiard balls. They exist in states of probability, governed by equations that defy our everyday intuition. The Schrödinger equation, for instance, allows us to predict the likelihood of finding a particle in a particular place. It's a mathematical framework that reveals the strange, counterintuitive nature of reality, where particles can be in two places at once or disappear and reappear in ways that seem impossible. One of the most remarkable things about mathematics is its ability to predict the unknown. When Paul Dirac combined the equations of quantum mechanics and special relativity, he stumbled upon a solution that suggested the existence of antimatter, a discovery that was later confirmed experimentally. Similarly, the equations of string theory, though still unproven, propose the existence of extra dimensions and vibrating strings as the building blocks of reality. These predictions push the boundaries of our imagination, showing that mathematics isn't just a reflection of the universe, it's a guide to what might lie beyond our current understanding. Yet, for all its power, mathematics also poses profound questions. Why does it work so well? Is mathematics something we invented, or is it an inherent part of the universe waiting to be discovered? These questions don't just belong to mathematicians, they invite all of us to ponder the nature of reality itself. As we continue to explore the cosmos, mathematics remains our most trusted compass. It connects the smallest particles to the largest galaxies, the earliest moments of the Big Bang to the distant future of the universe. And in that journey, we're reminded that the universe isn't just a collection of stars and planets, it's a symphony of numbers, equations, and patterns waiting to be decoded. Through mathematics, we're not just observers of the cosmos, we're participants in its grand, unfolding story. Cosmology, at its core, isn't just a science, it's a profound exploration of existence itself. While equations and telescopes help us map the stars, it's the philosophical questions that push us to dig deeper, to ask not just how the universe works, but why it exists at all. What is the nature of reality? Does the cosmos have a purpose? And where do we, as conscious beings, fit into this vast, intricate tapestry? These are the kinds of questions that have fascinated thinkers for millennia, and they're just as relevant today as they were to the ancient Greeks or the philosophers of the Enlightenment. At the heart of this intersection between philosophy and cosmology lies the concept of existence. When we look at the night sky, we're not just seeing points of light, we're witnessing the remnants of stars that lived and died billions of years ago, their light traveling across the cosmos to reach us. This raises a profound question. What does it mean for something to exist? Is existence defined by what we can observe, or is there more to reality than meets the eye? Take dark matter, for example. We can't see it, touch it, or directly measure it, yet its gravitational effects tell us it's there. Does that make it any less real? Philosophers and scientists alike grapple with these questions, reminding us that reality might be far stranger and more layered than we've ever imagined. Then there's the question of purpose. Does the universe have a goal, a direction, or is it simply the result of random chance? Some argue that the fine-tuning of the cosmos, the precise constants and conditions that allow life to exist, points to an underlying purpose. Others see it as a cosmic coincidence, a lucky roll of the dice in an infinite multiverse. This debate isn't just academic, it touches on our deepest hopes and fears about our place in the universe. Are we here by accident, or are we part of something greater? These questions don't have easy answers, but they invite us to reflect on the meaning of our own existence. Reality itself is another frontier where science and philosophy collide. What we perceive as reality might only be a small slice of a much larger picture. Quantum mechanics, for instance, challenges our everyday understanding of how the world works, suggesting that particles can exist in multiple states at once until observed. This idea, known as the observer effect, blurs the line between the observer and the observed, raising questions about the role of consciousness in shaping reality. Could it be that the universe only comes into being when we look at it? It's a question that feels more like philosophy than physics, yet it's rooted in cutting-edge science. These philosophical inquiries don't just challenge our understanding of the universe, they also shape the way we approach science itself. For example, the Anthropic Principle, which suggests that the universe must be compatible with the conscious life that observes it, has sparked debates about whether we're seeing the universe as it truly is or through a lens shaped by our own existence. It's a reminder that our tools, from telescopes to equations, are extensions of our curiosity, but they're also limited by the very nature of what it means to be human. In the end, cosmology and philosophy are two sides of the same coin. They both seek to answer the biggest questions we can ask, using different tools but driven by the same sense of wonder. Whether we're peering through a telescope or pondering the nature of existence, we're engaging in a timeless pursuit, one that connects us to the thinkers of the past and the explorers of the future. And in that pursuit, we're not just uncovering the secrets of the universe, we're also discovering what it means to be human in a cosmos that's infinitely vast, endlessly mysterious, and beautifully interconnected. Across the globe, the night sky has always been more than just a canvas of stars. It's a source of wonder, inspiration, and storytelling. Long before telescopes and satellites, ancient cultures looked up and saw not just lights in the darkness, but a tapestry woven with myths, gods, and cosmic tales. These stories, passed down through generations, offer a fascinating glimpse into how different societies have interpreted the universe and our place within it. Take, for example, the Aboriginal Australians, whose connection to the cosmos stretches back tens of thousands of years. For them, the stars are not just distant objects, but a living map of their ancestral journeys. The Milky Way, known as the emu in the sky, is a central figure in their Dreamtime stories, representing the spirit of creation and the cycle of life. This perspective doesn't just describe the universe, it embeds it within a cultural and spiritual framework, showing how the cosmos and human existence are deeply intertwined. In Norse mythology, the universe begins with a vast, primordial void called Ginnungagap, where fire and ice collide to form the first giant, Ymir. From his body, the world is shaped, with his skull becoming the sky and his brain the clouds. This vivid imagery reflects a world where chaos and creation are two sides of the same coin, a narrative that resonates with modern ideas of cosmic expansion and the interplay of forces that shape the universe. Meanwhile, in Hindu cosmology, the universe is seen as a cyclical entity, endlessly expanding and contracting in a rhythm of creation and destruction. The concept of Brahma's day and night describes vast cosmic cycles, each lasting billions of years, where universes are born, evolve, and dissolve, only to begin anew. This cyclical view mirrors some of the theories in modern cosmology, such as the Big Bounce, where the universe undergoes endless cycles of expansion and collapse. It's a striking example of how ancient wisdom can echo through the ages, offering insights that feel remarkably relevant today. The ancient Greeks also had their own cosmic narratives, with the philosopher Anaximander proposing that the universe emerged from an infinite, boundless substance called the apeiron. This idea of an infinite, ever-evolving cosmos predates modern scientific thought by millennia, yet it captures the essence of ongoing exploration and discovery. These cultural perspectives aren't just historical curiosities. They're a testament to humanity's enduring fascination with the cosmos. They remind us that science and storytelling are not opposites but complementary ways of understanding the universe. While science gives us the tools to measure and analyze, these ancient narratives offer a different kind of insight, one that connects the cosmos to our shared human experience. What's particularly striking is how these diverse stories often grapple with the same fundamental questions. Where did we come from? What is our place in the universe, and what does it all mean? Whether it's the aboriginal emu in the sky or the Hindu cycles of creation, these narratives reveal a universal desire to make sense of the unknown, to find patterns and meaning in the vastness of existence. As we explore these cultural perspectives, we're reminded that the story of the universe isn't just about physics and equations. It's also about imagination, creativity, and the human spirit. These ancient tales enrich our understanding, offering alternative ways of seeing the cosmos that are as profound as they are beautiful. And in that exploration, we're not just learning about the universe, we're also discovering the incredible diversity of human thought and the timeless ways we've sought to connect with the stars. The universe is a delicate balancing act, a cosmic dance where the tiniest change to the laws of physics could have made life impossible. Imagine for a moment if gravity were just a bit stronger, stars would burn out too quickly, leaving no time for planets to form. Or if the force holding atomic nuclei together were slightly weaker, complex elements like carbon, essential for life, might never have existed. These precise conditions have led many to wonder, is the universe finely tuned for life, or is it all just a cosmic coincidence? This is the heart of the Anthropic Principle, a concept that bridges science and philosophy, challenging us to think deeply about the nature of existence. At its core, the Anthropic Principle suggests that the universe's laws and constants appear fine-tuned because if they weren't, we wouldn't be here to observe them. It's a bit like finding yourself in a room with just the right temperature, lighting, and oxygen levels, conditions that seem tailor-made for your comfort. But did someone design the room that way, or is it simply the only room where you could exist? This principle doesn't claim to answer the why of the universe's fine-tuning. Instead, it invites us to consider the implications of what we observe. One way to approach this idea is through the lens of the multiverse. If our universe is just one of countless others, each with its own set of physical laws, then it's not surprising that at least one of them would have the right conditions for life. In this view, the fine-tuning we see isn't evidence of design, but rather the result of probability, a cosmic lottery where we happen to win the jackpot. It's a perspective that shifts the question from why is the universe this way to why are we here to ask the question, but not everyone is satisfied with this explanation. Some argue that the precision of the universe's constants points to something more intentional. The gravitational constant, the strength of electromagnetism, the mass of particles, these aren't arbitrary numbers. They're finely calibrated in ways that allow stars to shine, planets to form, and life to emerge. For some, this suggests the possibility of a deeper intelligence or purpose behind the cosmos, a notion that resonates with both scientific curiosity and philosophical wonder. What makes the Anthropic Principle so compelling is that it doesn't just belong to scientists, it's a question that invites everyone to reflect on their place in the universe. Are we the result of a cosmic accident, or is there something more profound at play? The answer, if there is one, remains elusive, but the journey to explore it is filled with awe and discovery. As we ponder these questions, we're reminded that the universe is more than just a collection of stars and galaxies. It's a stage where life, consciousness, and curiosity have emerged to observe and question its mysteries. Whether the universe is finely tuned by chance or design, the fact that we're here to explore it is a testament to the incredible complexity and beauty of existence. And in that exploration, we're not just uncovering the secrets of the cosmos, we're also uncovering the boundless potential of our own curiosity to imagine, question, and dream. What if everything we know, our lives, the stars, even the laws of physics, isn't real? What if the universe, as vast and intricate as it seems, is nothing more than an elaborate simulation? This isn't the plot of a sci-fi movie. It's a serious question that scientists, philosophers, and technologists are grappling with today. Known as the simulation hypothesis, this idea suggests that our reality might be a computer-generated construct, an artificial creation designed by some advanced civilization. It's a thought that challenges our most fundamental assumptions about existence, and it's gaining traction in ways that are hard to ignore. The roots of this idea stretch back centuries, with philosophers like René Descartes pondering whether our perceptions of reality could be deceiving. But in recent years, the simulation hypothesis has moved from philosophy to the forefront of scientific discourse, thanks in part to rapid advancements in technology. Consider this: if humanity continues to progress, we might one day create simulations so advanced that they're indistinguishable from reality. If that's possible, what's to stop us from being in a simulation ourselves? This reasoning, popularized by figures like Elon Musk and philosopher Nick Bostrom, suggests that the odds of us living in a base reality, the real universe, are incredibly slim. From a scientific perspective, the simulation hypothesis isn't just a thought experiment. It's a framework that could explain some of the universe's deepest mysteries. Take quantum mechanics, for example. At the smallest scales, particles behave in ways that seem almost programmed, existing in multiple states until observed. Could this be a sign that the universe runs on a kind of computational code, like a cosmic software program? Some researchers are even exploring whether there might be glitches or patterns in the fabric of reality, tiny anomalies that could hint at a simulated universe. But the implications of this idea go far beyond science. If we're living in a simulation, what does that mean for concepts like free will, morality, and the meaning of life? Are our choices our own, or are they pre-programmed by whatever entity created the simulation? These questions blur the lines between philosophy and science, inviting us to rethink not just how the universe works, but who we are within it. Of course, not everyone is convinced. Critics argue that the simulation hypothesis is untestable, a fun idea, but one that lacks empirical evidence. After all, how could we ever prove we're in a simulation if it's designed to be indistinguishable from reality? Others see it as a modern-day version of ancient myths, a way for humans to grapple with the unknown by framing it in terms of our own technological achievements. Yet, even as a speculative idea, the simulation hypothesis has value. It pushes us to question our assumptions, to explore new ways of thinking about the universe and our place within it. Whether or not we're living in a simulation, the very act of considering this possibility reminds us of the boundless nature of human curiosity. It's a reminder that the universe is full of mysteries, some of which might be hiding in plain sight, waiting for us to look closer. As we explore this provocative idea, we're not just debating the nature of reality, we're engaging in a conversation that stretches across disciplines, cultures, and centuries. It's a conversation that challenges us to think bigger, to imagine possibilities beyond what we've ever known. And in that conversation, we're reminded that the universe, whether real or simulated, is a place of endless wonder waiting for us to uncover its secrets. Time travel has captivated the human imagination for centuries, from the pages of H.G. Wells' The Time Machine to the blockbuster adventures of Back to the Future. But beyond the realm of science fiction, could time travel actually exist? To answer this, we need to dive into the physics of time itself, a concept that's far stranger and more malleable than we often assume. Let's start with the basics. Time, as we experience it, flows in one direction forward. This is known as the arrow of time, a concept rooted in the second law of thermodynamics, which states that entropy or disorder always increases. But what if this flow isn't as fixed as it seems? Einstein's theory of relativity offers a tantalizing possibility. According to relativity, time isn't an absolute constant. It's a dimension that can stretch, twist, and even loop under the right conditions. This means that under extreme circumstances, like near a black hole or at speeds approaching the speed of light, time can behave in ways that defy our everyday experience. One of the most intriguing ideas in this realm is the concept of wormholes, theoretical tunnels through space-time that could connect two distant points in space and time. Imagine folding a piece of paper so that 2 points touch. A wormhole would be like punching a hole through that fold, creating a shortcut. While wormholes are mathematically possible according to Einstein's equations, there's a catch. They would require exotic matter with negative energy to stay open, something we've never observed. Without it, these cosmic shortcuts would collapse almost instantly. Then there's the idea of closed time-like curves, or CTC, paths through space-time that loop back on themselves, allowing an object or person to return to their own past. This concept emerges from solutions to Einstein's equations, particularly in the context of rotating black holes or certain configurations of spacetime. One famous example is the Gödel universe, a hypothetical model where the entire cosmos rotates, creating conditions where time travel could theoretically occur. However, like wormholes, CTCs come with their own set of challenges, including the potential for paradoxes like the infamous grandfather paradox, where a time traveler could prevent their own existence. So, is time travel possible? The answer, for now, is a cautious maybe. While the math allows for these possibilities, the practical hurdles are immense. Exotic matter, the stability of wormholes, and the energy requirements for manipulating space-time are just a few of the obstacles standing in the way. And let's not forget the philosophical questions. If time travel were possible, why haven't we met any time travelers from the future? But perhaps the most fascinating aspect of this exploration isn't whether time travel is achievable, it's how it reshapes our understanding of time itself. Time, once seen as a rigid, unchanging force, is now understood as a dynamic, flexible dimension woven into the fabric of space-time. Whether or not we ever build a time machine, the journey to understand time's mysteries is a journey into the very heart of the universe, where the boundaries between past, present, and future blur into a single, interconnected tapestry. As we ponder these possibilities, we're reminded that the universe is far more than a collection of stars and planets. It's a stage where the laws of physics dance with the limits of our imagination. And in that dance, time travel isn't just a scientific question. It's a gateway to exploring the endless possibilities of existence itself. Imagine this. Every time you make a decision, whether it's choosing coffee over tea or taking a different route to work, a new version of reality splits off, creating a parallel universe where the other choice played out. This isn't just a plot twist from a sci-fi movie. It's a serious scientific concept known as the Multiverse Theory. The idea that our universe might be just one of countless others, each with its own unique timeline, challenges everything we think we know about reality, identity, and even free will. At the heart of this concept is the many worlds interpretation of quantum mechanics. In the quantum world, particles don't behave like tiny billiard balls. They exist in a state of probability where multiple outcomes are possible until observed. The many worlds interpretation takes this a step further, suggesting that every possible outcome actually happens, it's just that each one occurs in a separate, branching universe. So, in one universe, you might have taken that job offer across the country, while in another you stayed put. Both realities exist, unfolding simultaneously but independently. This idea raises fascinating questions about identity. If there are infinite versions of you, each shaped by different choices and experiences, what does that mean for the concept of you? Are these parallel selves still you, or are they entirely separate beings? Philosophers and scientists alike grapple with this question, as it challenges our understanding of individuality and continuity. In a multiverse, the idea of a singular, unchanging self becomes far more complex, if not entirely elusive. Then there's the question of free will. If every possible decision creates a new universe, does that mean our choices matter less, since all outcomes are realized somewhere? Or does it make them matter more, because each decision spawns an entirely new reality? Some argue that the multiverse actually strengthens the case for free will, as every choice we make has real, tangible consequences, just not necessarily in the universe we currently inhabit. But how real is the multiverse? While the many worlds interpretation is mathematically sound, it's also notoriously difficult to test. Unlike black holes or exoplanets, which we can observe indirectly, parallel universes are, by definition, beyond our reach. They don't interact with our universe, making them impossible to detect with current technology. This has led some critics to dismiss the multiverse as speculative or even unscientific. Yet, for all its challenges, the multiverse theory offers a compelling framework for understanding some of the universe's biggest mysteries. For instance, it provides an elegant solution to the fine-tuning problem, the idea that the constants of nature seem perfectly calibrated for life. If there are infinite universes, each with different physical laws, it's not surprising that at least one of them would have the right conditions for life to emerge. What makes the multiverse so captivating isn't just its scientific implications, it's the way it stretches our imagination. It invites us to think beyond the boundaries of our own reality, to consider a cosmos far more vast and varied than we've ever imagined. Whether or not parallel universes exist, the very idea challenges us to rethink our place in the universe and the nature of existence itself. As we explore this mind-bending concept, we're reminded that the universe is full of mysteries waiting to be uncovered. The multiverse isn't just a scientific theory, it's a window into the infinite possibilities of reality, a reminder that the cosmos is far stranger and more wonderful than we've ever imagined. And in that exploration, we're not just rewriting the story of the universe, we're also discovering the boundless potential of human curiosity to dream, to question, and to imagine the unimaginable. The future of space exploration isn't just about rockets and rovers, it's about expanding the boundaries of what humanity can achieve. Right now, we're standing on the brink of a new era, one where the dream of living on other planets is no longer confined to science fiction. Take Mars, for example. NASA's Artemis program is paving the way for a sustainable human presence on the Moon, serving as a stepping stone for future missions to the Red Planet. Meanwhile, private companies like SpaceX are working on Starship, a fully reusable spacecraft designed to carry humans to Mars and beyond. These efforts aren't just about planting flags, they're about building the foundations for a multi-planetary future. But Mars is just the beginning. Beyond our solar system, the possibilities are even more staggering. Interstellar travel, once the stuff of fantasy, is now being seriously explored. Breakthrough Starshot, for instance, aims to send tiny, light-powered probes to Alpha Centauri, the nearest star system to Earth. These probes, traveling at a fraction of the speed of light, could reach their destination in just over 20 years, sending back data that would revolutionize our understanding of distant worlds. While the technical challenges are immense, the mere fact that we're considering such missions shows how far we've come in our quest to explore the cosmos. Closer to home, missions to the outer planets are also set to transform our understanding of the solar system. Europa Clipper, scheduled to launch in the coming years, will investigate Jupiter's icy moon Europa, which is believed to harbor a subsurface ocean. Could this ocean support life? The answer could redefine our understanding of where life can exist. Similarly, NASA, a Dragonfly mission, will send a drone-like rotorcraft to explore Titan, Saturn's largest moon, where rivers of liquid methane flow across a landscape that feels both alien and eerily familiar. These missions aren't just about discovery, they're about challenging our assumptions and uncovering the potential for life in the most unexpected places. As we look ahead, it's clear that the future of space exploration isn't just about technology, it's about collaboration. International partnerships, like the one behind the International Space Station, are becoming increasingly important. China's space program, for instance, is making strides with its Tiangong space station and ambitious plans for lunar exploration. Meanwhile, the European Space Agency is working on missions to study dark energy and map the Milky Way in unprecedented detail. These collaborative efforts remind us that space exploration is a shared human endeavor, one that transcends borders and unites us in our curiosity about the universe. What's truly exciting is how these missions will shape our understanding of the cosmos. Every discovery, every piece of data, adds another layer to the story of the universe. Whether it's finding evidence of life on another world, mapping the structure of distant galaxies, or testing the limits of human ingenuity, the future of space exploration is a journey of endless possibilities. And as we take these next steps, we're not just exploring space, we're also discovering what it means to be human in a universe that's infinitely vast, endlessly mysterious, and full of potential. This is a future where the stars aren't just points of light in the sky, they're destinations. And with every mission, we're moving closer to making that future a reality. As humanity's reach extends further into the cosmos, we're not just facing scientific and technical challenges, we're also grappling with profound ethical questions. What responsibilities do we have as we explore new worlds? How do we balance our ambitions with the need to preserve the integrity of the universe? These aren't just philosophical musings, they're urgent considerations as we prepare to mine asteroids, colonize other planets, and potentially encounter extraterrestrial life. One of the most pressing ethical dilemmas is planetary protection. Imagine sending a rover to Mars or a probe to Europa, only to accidentally introduce earthly microbes that could contaminate these pristine environments. This isn't just a hypothetical concern, it's a real risk that could jeopardize our ability to study these worlds in their natural state. Planetary protection protocols exist to prevent such contamination, but as missions become more frequent and ambitious, the stakes are higher than ever. How do we ensure that our exploration doesn't inadvertently harm the very places we're trying to understand? Then there's the question of space mining. Asteroids and moons are rich in valuable resources like rare metals and water, which could fuel future space missions and even life on Earth. But who gets to claim these resources? Is it fair for a single nation or corporation to profit from the exploitation of celestial bodies? Or should these treasures be shared for the benefit of all humanity? The Outer Space Treaty of 1967 prohibits nations from claiming sovereignty over celestial objects, but it's silent on the issue of resource extraction. This legal gray area has sparked debates about equity, sustainability, and the potential for a new kind of space race, one driven by profit rather than discovery. Perhaps the most profound ethical question of all revolves around the rights of potential extraterrestrial life. If we discover microbes on Mars or fish-like creatures in Europa's oceans, how should we treat them? Do they have rights, and if so, what are they? The idea of extraterrestrial rights might sound like science fiction, but it's a serious consideration for astrobiologists and ethicists alike. After all, if life exists beyond Earth, it would fundamentally change our understanding of our place in the universe and our responsibilities to it. These ethical challenges don't have easy answers, but they're essential to address as we step into the next frontier. Space exploration isn't just about what we can do, it's about what we should do. It's a reminder that our actions in the cosmos have consequences, not just for us, but for the universe itself. As we navigate these complex questions, we're not just exploring space, we're also exploring what it means to be ethical explorers. It's a journey that challenges us to think beyond our own interests, to consider the broader impact of our actions, and to strive for a future where the stars are not just places to visit, but places to protect and cherish. And in that journey, we're reminded that the universe is more than just a collection of planets and stars. It's a shared heritage, one that we have a responsibility to preserve for generations to come. Earth's climate is undergoing dramatic changes, but to truly understand its significance, we need to zoom out, way out, and see our planet as part of a much larger cosmic narrative. While climate change is often framed as a local or even global issue, its roots and implications stretch far beyond our atmosphere, connecting us to the broader dynamics of the universe itself. At the heart of this connection is the Sun, the ultimate driver of Earth's climate. Our star's energy fuels the weather systems, ocean currents, and even the delicate balance of greenhouse gases that make life possible. But the Sun isn't static. It's a dynamic, evolving body with cycles of activity that influence our planet in profound ways. For instance, periods of increased solar activity can amplify Earth's temperatures, while quieter phases can lead to cooling trends. Understanding these solar cycles isn't just about predicting space weather. It's about seeing how Earth's climate is part of an intricate dance with the cosmos. But the Sun isn't the only cosmic player in Earth's climate story. Over millions of years, our planet's orbit and tilt have shifted in predictable patterns known as Milankovitch cycles. These subtle changes alter how much sunlight reaches Earth, triggering ice ages and warmer interglacial periods. It's a reminder that even within the stability of our solar system, long-term climate shifts are a natural part of Earth's history. What's different today, however, is the speed and scale of change. Human activity has dramatically altered the composition of our atmosphere, accelerating processes that would normally take millennia. This raises an important question. If Earth's climate is influenced by cosmic forces, how do we balance our understanding of natural cycles with the urgency of human-driven change? To answer this, we can look to other planets for clues. Venus, for example, is a cautionary tale of a runaway greenhouse effect, where thick clouds of carbon dioxide trap heat, creating a surface hot enough to melt lead. Mars, on the other hand, lost much of its atmosphere, leaving it cold and barren. These neighboring worlds show us the extremes of planetary climate systems, highlighting the delicate balance that makes Earth uniquely habitable. Looking even further, the study of exoplanets' worlds orbiting other stars offers insights into how atmospheres evolve over time. Scientists are discovering planets with climates that range from scorching hot to freezing cold, each shaped by their distance from their star, the composition of their atmosphere, and even the influence of cosmic events like supernova. These discoveries remind us that climate isn't just an Earth-bound concern. It's a universal phenomenon woven into the fabric of planets across the galaxy. So, what does this mean for our future? On one hand, the cosmic perspective reminds us that change is a natural part of planetary evolution. On the other, it underscores the fragility of Earth's climate and the profound responsibility we have to protect it. By studying the interplay between planetary science and cosmology, we gain not just a deeper understanding of our place in the universe, but also the tools to navigate the challenges ahead. Climate change isn't just an Earth story, it's a cosmic one. It connects us to the rhythms of the sun, the cycles of our solar system, and the broader dynamics of the universe. And as we work to address the challenges of a warming planet, we're not just shaping the future of Earth, we're also contributing to the ongoing story of life in the cosmos. It's a story that began billions of years ago, and one that we have the power to continue writing with care, curiosity, and a deep respect for the delicate balance that sustains us all. Rewriting the story of the universe isn't a solo endeavor, it's a collective journey, one that spans the globe and unites minds from every corner of human knowledge. Imagine a symphony where physicists, astronomers, engineers, philosophers, and even artists come together, each contributing their unique expertise to compose a deeper understanding of the cosmos. This collaborative effort isn't just a nice-to-have, it's essential. The universe doesn't reveal its secrets easily, and no single field of study can tackle its mysteries alone. Take, for example, the discovery of gravitational waves in 2015. This groundbreaking achievement wasn't the work of a single team or even a single country. It was the result of decades of collaboration between scientists, engineers, and institutions across the world. From the laser interferometers in the United States to the data analysis teams in Europe, each piece of the puzzle had to come together perfectly to detect ripples in space-time caused by colliding black holes. It was a triumph not just of technology but of teamwork, a reminder that the biggest breakthroughs happen when we work together, but collaboration goes beyond science. The story of the universe is also shaped by cultural perspectives, from ancient myths that interpret the stars to modern art that visualizes black holes. When we bring these diverse viewpoints into the conversation, we enrich our understanding and see the cosmos through new lenses. For instance, indigenous knowledge systems, like those of the Aboriginal Australians or the Navajo, offer profound insights into how humans have connected with the cosmos for millennia. These traditions remind us that science isn't the only way to engage with the universe, it's one of many. Even within the scientific community, collaboration is key. Cosmologists rely on particle physicists to understand the building blocks of matter, while computer scientists develop algorithms to sift through mountains of data. Biologists explore the potential for life on other planets, and engineers design the spacecraft that carry our instruments into the void. Each discipline brings its own tools and perspectives, creating a richer, more nuanced picture of the cosmos. What's truly remarkable is how this spirit of collaboration transcends borders. In an era where geopolitical tensions can divide us, space exploration remains a rare area of global unity. The International Space Station, for example, is a testament to what humanity can achieve when we set aside our differences and work toward a common goal. It's not just a laboratory in orbit, it's a symbol of what's possible when we come together. As we rewrite the story of the universe, we're reminded that this isn't just about science, it's about humanity. It's about our shared curiosity, our collective ingenuity, and our ability to dream beyond the limits of what we know. Every discovery, every theory, every new piece of the puzzle is a testament to the power of collaboration. And as we continue this journey, we're not just uncovering the secrets of the cosmos, we're also discovering what we can achieve when we unite as a species. This global effort is more than just a scientific endeavor, it's a celebration of what makes us human. It's a story of curiosity, creativity, and connection, written not by one person but by all of us. And in that story, we're not just observers of the universe, we're active participants, shaping its narrative with every question we ask and every answer we find. The universe, as we've come to understand it, is anything but static. It's a living, breathing entity, constantly evolving and revealing new layers of complexity. What started as a single, unimaginably dense point has unfolded into a cosmos teeming with galaxies, stars, planets, and the potential for life. Yet, for all we've discovered, from the Big Bang to the multiverse, from dark matter to the holographic principle, one thing is clear: the story of the universe is far from over. Every breakthrough, whether it's a new telescope image or a groundbreaking theory, doesn't just answer questions, it sparks new ones. The more we learn, the more we realize how much remains unknown. It's like peeling an onion. Each layer reveals another, more intricate one beneath. But here's the beauty of it: this endless exploration isn't just for scientists. It's for all of us, whether you're gazing at the night sky, reading about the latest discoveries, or simply pondering the mysteries of existence. You're part of this grand journey. This journey isn't just about uncovering facts, it's about connecting with something greater than ourselves. The universe invites us to dream, to question, and to imagine. It challenges us to think beyond our everyday lives and consider the infinite possibilities that lie beyond. And in doing so, it reminds us of our shared humanity. No matter where we come from or what we believe, we all look up at the same stars, wonder about the same mysteries, and share the same curiosity that drives us forward. As we wrap up this exploration, remember that the universe's story is still being written, and you're a part of it. Every observation, every question, every moment of awe contributes to this ongoing narrative. So keep looking up, keep asking questions, and keep exploring. The cosmos is vast, but so is our capacity to understand it. Thank you for joining us on this incredible journey through the wonders of the universe. If you enjoyed this video, don't forget to like, subscribe, and share your thoughts in the comments below. What fascinates you most about the cosmos? What questions do you still have? Let's keep the conversation going. Until next time, stay curious and keep reaching for the stars.